and have been part of a graph analytics team. We had been building a Python open source Python library for everything deep learning on graph structured data. And I will briefly touch upon why such a tool was needed and the promise of it, and where it's we're hoping that it will be something that will be much more widely used because it's applicable to a number of applications in real world. So on that, let's just start with where do we actually even for that. So let me just briefly mention overall what I am planning to talk about. Hopefully, we will be able to manage to cover all of these things, and hopefully you guys will be able to retain some of the information I'm going to be sharing with you. So overall, the first thing is that should we even care about network structured data overall? Why is it even relevant? So I will give you some real world examples of where graphs and networks are very prevalent, and we see it every day. And pretty much like every one of us is using them in one way or the other. And then I would, just for the sake of, so that we are on the same page, I will briefly mention some of the key concepts behind graphs so that when I'm talking about them, it's clear in everyone's mind what they are about. Then I will touch upon the main machine learning tasks that you can do with graphs. And then I will start into what graph machine learning is about and expand on graph convolutions, which are the main building blocks for deep learning or graph learning on graphs. I will walk you through two interesting examples. One is from Twitter about classification of nodes as hateful and non-hateful users, and then I will lastly talk about one of my very recent work with Sydney Transport, Transport for New South Wales, which is Sydney's main traffic management system, about building a system for them for forecasting traffic conditions using graph convolutions and LSTMs. So it's a very exciting project, and I think one of the very promising area where graph machine learning is highly applicable. Okay, so I will start with where do we actually see networks in our real life. So I think social networks, something every one of us in one way or the other is using, and we see that the data there is all networks. So you have individuals who are users, and then based on the application, there are relationships between them. So if you think about Twitter, you have users, and then what they are tweeting, who they're following, who they are connected to, are all examples of the network they have. Similarly, in LinkedIn, who you're connected to is is going to create a network. Facebook, I think I don't even need to explain how connections, friendships, etc. work there. Pretty much everyone at one point or the other have used Facebook or maybe still using it. So yeah, that's one of the main examples. Transport, as I mentioned about Sydney Transport for New South Wales, I have been part of another project, with Sydney Trains Network, about building a system for frequency of service prediction. So this is a network of complete Sydney train systems with all the different colors indicating different lines, and you have all these connections. And the question is, how can we forecast frequency of services on those kind of networks? So another application that I just recently, we did a proof of concept with them, and starting a next phase of it in November. Otherwise, something in academia you probably come across all the time, citation networks. So which papers are citing which other papers create a network. So each paper is a set of, let's say, set of words, and then they cite other papers who have similar topics. So that create connections. Protein-protein interactions are highly relevant, and I think one of the very promising areas where networks and deep learning on networks is really applicable. So, for example, protein-protein interaction network for schizophrenia are used to understand what are the functional protein loci that are responsible for a disorder like schizophrenia. And otherwise, another application that is highly relevant for this whole paradigm of deep learning on graphs is financial transactions. So basically, which are fraudulent transactions, which are questions of money laundering, tax evasion. All of them are something that are something a number of financial bodies are interested in, governments are interested in. So this is, for example, the data from Panama Papers leak, which primarily deals with the offshore companies different organizations or individuals have created in tax havens to avoid taxes, and there had been tons of studies done on how to analyze these kind of transaction networks to find to investigate who is avoiding taxes, who is hiding money, etc. So basically, tons of very interesting applications in networks and tons of really interesting questions around networks that can be answered through methods in deep learning or machine learning. Now, just in a couple of slides, what do we mean by network or graphs? Usually, we visualize a network as a set of nodes, which are these blobs. They're called nodes, vertices, entities, and a whole bunch of things, but typically node and vertices, and they are connected through edges or links. Depending on which application we're talking about, sometimes you would call them edge, sometimes you would call them link. So a social network like Facebook, you would call them friendship links, or an edge could be just two road segments connected through a central point, etc. Similarly, graphs and networks are interchangeable terms, and I probably will be switching between one or the other. So just don't get confused; they mean the same thing. Now, both the nodes and the edges can be of different types in a single network. So you could have, let's say, a set of individuals and a set of movies, and which individual watch which movie. So the individuals or people will be nodes, and movies are also nodes, and then the edges between them is which person is watching which movie. So you could have networks where you have different types of nodes, and you can similarly have different types of edges as well. So these are called heterogeneous graphs. And it's important to mention this thing because in real world, usually we don't have a very complete picture of one network. So we are what we have in its place is different types of networks, and we use that information together to come up with any answer. So just to give you an idea that these kind of methods are not just applicable to a very simple graph with one set of entities and one kind of relationship, but it could be a diversity of nodes, and node or vertices types or entity types, and a diversity of edges as well. And then just the way we have in standard machine learning, we have node and edge attributes. So node attributes, which is similar to what we see in typical machine learning, which is basically the properties or features associated with each entity. So for example, that could be a location as an example for the traffic network. It could be where the road segment is located, its GPS location, etc. Or it could be for an entity like a person, it could be their age, gender, etc. So these are all the node attributes. And usually, like forget about network, but generally whenever you have machine learning, you typically have some kind of attributes or features that you are using to build or train a model. Similarly, now analogous to the node attributes, when we have a network for edges as well, we can have attributes. So we can have, for example, time. We can have, let's say, strength of a friendship somehow. That could be a measure, or the frequency of transactions could be another way to imagine what could be a property or an attribute of an edge. Now, the next question is, so what kind of machine learning tasks can we do on graphs? So pretty much what you could do with machine learning without a graph, you can do it with graphs. But then there's some other very interesting questions that can be that are very well suited for a graph structured data, or could be better answered with graphs, and are extremely challenging without them. So to start with, the standard machine learning tasks like predicting attributes. So it could be a node level attribute, or it could be an edge attribute in case of a graph. So for node, for example, in this graph on the right, for example, if we want to know that if an individual is dodgy or not, we can, based on a certain set of features, we train a model to be able to predict whether these characteristic leads to are indicative of a person being fraudulent or not. Similarly, you could do the same for edges as well. So if you have a transaction network and you want to know that if, for example, a credit card transaction is fraudulent or not, you could be predicting those that property. So when I say prediction, it's basically covers prediction as well as classification, because classification is in of itself is a kind of a prediction. You are, if you're trying to classify your entities into a number of groups, there you're basically predicting one of their attributes. So I just kept it generic. Predict relationships. So that's one thing is that what's the attribute of a relationship, but on the other hand, so which was, as an example I gave, like whether a transaction is fraudulent or not. So that's basically predicting the label. But another interesting part about graph machine learning is that it's transductive, that you could actually fill in the missing information. So if there are missing links, you are able to predict those as well. That, for example, you don't know if two individuals has, for example, had any connection, a phone call or something, or are they associated with each other. You could predict those links as well. So usually, like I'm not very comfortable with those applications, but this is the kind of area where you want to build the incomplete network. So, for example, if you have if you're trying to, in the application of, for example, terrorism, you're interested in finding out that what are the missing links, who was the individual talking to. These are the sort of applications where this sort of link prediction is highly applicable and used or talked about. At least it's a very challenging problem, but something that a lot of government agencies, for example, are really keen on understanding better. Similarly, finding similar entities, that's a very interesting problem, and that's actually more relevant to machine learning on graphs, and is better suited for applications where you have a graph data. So this is a sort of a problem where you want to see structural equivalences. So you want to see that certain types of individuals have similar connections. So, for example, if you have organizational charts, you can see that whether a managerial post will have a certain kind of a structure surrounding that role. So, a vice president will have certain individuals that they are connected to, who are their subordinates, and so on and so forth. So, you could so where you have these connections, these type of applications are meant to find similarity about classes of individuals. So it's not just about an individual, but basically what are the structurally similar individuals. So who are, for example, individuals at the vice president level, who are at the group leader level, who are the team lead levels, and so on and so forth. And as you can see, that those are the sort of applications where a graph structure is going to be a lot more useful than just having a set of attributes associated with each entity. Another application where graph machine learning or learning on graphs in general has been used in practice a lot is entity resolution. So this is the question of when you have one individual with multiple identities, how do you resolve that they are the same individuals? And you would wonder, why would individuals will have multiple identities? So I'll go back to that Panama paper leaks. So in Panama Paper and Paradise Papers leaks, what we found out, by we I mean the investigative journalists who were doing all the digging, that that to avoid taxes, when individuals create these offshore companies, they would use various identities, so that they are the reason they would use various identities is because they don't want to be tracked. So they won't use their original name or their original address or something like this. So then the question is that when you want to be able to identify who's who, you need to have some system to understand that there is a pattern, similarity in patterns of how individuals are creating these companies. So for example, maybe they're always using a certain abbreviation in all the companies that they're creating. That could be one red flag that would tell you that they probably are the same individual. Sometimes people just misspell certain words, and that's again another way of identify who's who. But that's when you're just going as deep into just some language similarities. But then the structural similarities have been found to be really relevant in identifying or in resolving these discrepancies in various entities, etc. It's one of the applications that at least like in practice I've seen a lot being where graph machine learning is a lot being used. So yeah, these are the main tasks in graph machine learning. Now, just to give it a little, make it a little concrete, and actually I'll have a few other examples as well, just to highlight where machine learning and graphs is different from traditional machine learning. So the way I believe you guys have all had a flavor of machine learning one way or the other, but in general, the way you see it is machine learning as some kind of a set of features that are given to you in the form of a table, and then you have a whole bunch of samples, and the question is you typically have a target that you want to be able to predict using those features. So what you're doing is that given a set of features, you train a model or to fit in those features, and such that you calculate the weights, how they are going to help you calculate a target variable. So this would be a standard machine learning approach, right? Now, there is a certain underlying assumptions which over the time we keep on forgetting that why these method works, or what's the simplifying assumption behind them. The main assumption is that we assume that each entity is independent of the other. So basically, overall, if you have as many samples as you have, you assume that each sample is independent of the other. And so what you're doing is you're calculating the probability, or you're predicting each target based on the features of the individual entities, irrespective of what else is in your data set. And this actually works for the most part. So for example, in the previous example, when we were trying to predict the income of individuals, a simple thing is that, okay, we can use certain features, probably gender, age, and a number of other features to be able to predict that what could be the income of that target variable. What we don't care about is that whether one individual is connected to another individual. And usually these kind of, we don't have to think about these connectivity. Usually we assume that each entity is independent and represented by their independent set of characteristics. But this may not always be true. So for example, if so it may not always be true. So you could have connections between individuals. So for example, here at the bottom, I have a graph of the same sample data that I had on the previous slide. Now these and the black blobs are the individuals, and the connection between them are different relationships between them. So they could be colleagues, they could be living in the same neighborhood, or they could be familial ties between them. And they might be reflective of of the income of an individual. So for example, generally we assume that there won't be too much of income disparity in a given neighborhood. So if two individuals are living in the same neighborhood, if they are next door neighbor, we would the income of one individual could be reflective of the income of another individual. I'm just giving just one example it may not always be necessary, but we can see that this connectivity or this relationship information could be helpful in helping in improving our prediction. So then what do we do with this sort of information? Have we what would be the thought process behind, okay, how we can incorporate that neighborhood information or that relational information? Now, on the left of this, I have this individual in the center who is connected to various individuals, and these spirals indicate the degree of separation from every set of individual. Now, just keep that in mind, that when I talk about relationships, what these spirals indicate is that there could be different degrees of relationships. So you are, your friends, your colleagues are someone that you are nearest to you, that are somebody, they're the people you interact with on one-on-one basis, face-to-face, every day or very frequently. But then you also have friends of friends, or the family relationships of your colleagues, etc., and maybe you're the boss of your boss, etc., whom you don't talk directly very frequently, but still you're connected to a certain degree. And we can keep on going out in these circles, and can see that we have various levels of relationships. So having that picture in mind, the question is that how do we actually use all these different this sort of attributes while we are building a machine learning model? So in the beginning, the traditional analytics approaches were where graph structures were incorporated. These features these relationships were used as features. So basically, the way we have this stable view of our machine learning problem, you would further extend it by adding all the individuals in your network as other features, and maybe just add binary values 1 and 0, indicating whether you are connected to an individual or not, whether you know this person or not. And then, of course, if you go back to this spiral diagram, we could further extend it by saying that, okay, to what degree you're connected, so for example, how frequently you talk, and how close the relationships is, etc., could be another way to weight it. So this was, it looks natural, and it looks like, yeah, we can still go ahead with our traditional machine learning approaches and just have a much bigger table of features that we are using as our independent variables, or as our characteristics of individual to train a model on. However, this is highly challenging for a number of reasons. First of all, our table will be exponentially big, then it will be very sparse, because you at any given point very few people, but in any each sample data will maybe have thousands and millions of users maybe, and you have this unnecessary extra overhead of carrying all that empty rows, or empty columns, without adding much to it. Plus, it's not very flexible to incorporate the different degree of relationships. So, where if we talk about, maybe, we incorporate your direct friends, but then what happens when you have friends of friends, and the friends of friends of friends of friends, etc. So, it's very hard to scale this approach. So that's where graph machine learning the idea was originated, that how do we actually incorporate this structural information without touching the general feature table that we usually work with. So so the thought was that, okay, how do we actually just use the graph as it is, and just use it as a separate piece of information that is being fed into our machine learning model. So yeah, that was overall the idea behind that inspired this whole field of graph machine learning. And overall, just to summarize before we move on to the details of how it works, what so far I have hopefully tried to convey to you, and hopefully you have been able to retain a bit of it, is that what graph machine learning does is that it extends the general paradigm of machine learning on our table or attribute set of characteristic to a network structure. So what we are interested in is not just looking at individual characteristic, but how those individuals are related to each other. Similarly, we can do this kind of methods not just for one kind of a homogeneous kind of relationships or similar one type of entities, but but the field has advanced enough that we can actually incorporate multiple kind of relationships and multiple kind of entities. This is a highly popular research area in the last 5 or 6 years. It's just been one of the main, it's been catching up quite a bit in many of the main machine learning conferences. You would find now a lot of work done on graph machine learning, and it's just one of the hot topics. And me and my team have been building this tool called Stellargraph, which is an open source Python library for graph machine learning. The idea there was that usually what you find is that, yeah, this is a very hot topic. This is very, very relevant to a lot of applications. However, it's beyond academia. It's not very easy for a machine learning practitioner to use it. So, you know, how do we democratize the process? How do we actually make it available to be used by everyone? So just the way, you know, we have CNNs now, you know, in any pick up any popular machine learning framework like TensorFlow, Keras, etc., you would be able to easily build a complex CNN image detection model in few lines and a few minutes. So the same idea that, okay, how do we actually have methods that can work on graph structure data available for everyone? So this is where this library is, and do check it out. And it's it has a number of demos and quite easy to use. But and feel free to talk to me anytime if you're interested in any of the methods and are unable to get it up and running for any applications you're working on. So it is, so why is it, yeah, why do we, who actually cares about it beyond academia? So in industry, there have been numbers of applications where they have been used to recommender systems. So for example, any streaming platform, video streaming platform, they would be interested in recommending you videos or movies that you would actually want to watch, and they heavily rely on who you are connected to, who your friends are, who actually introduced you to a certain tool, for example, and they would use their information to be able to recommend you something. Twitter, a few years ago, acquired this company called Habibah AI. It's a UK company that built a tool for discriminating hateful and non-hateful user, and on a platform like Twitter, for a platform like Twitter, and using graph machine learning. So eventually, you know, Twitter just acquired them, and now they are actually productionizing that their concept into and incorporating it into Twitter application. Traffic prediction, something I had been involved with in the Sydney, in the Transport for TFNSW, Transport for New South Wales unit here in New South Wales. But otherwise, Google has a joint hand with DeepMind, which is another company. It's global, basically started in UK, but they do a lot of machine learning and especially graph machine learning work. And they are using, they're trying to improve Google travel time predictions based on graph convolution. So, you know, this is, the field is fairly new. However, it is now being used in very big organizations to improve their processes. All right, so now let's move on to what is exactly convolutions on graph, or convolutions in graph neural networks. So the idea actually is quite similar to what CNN does, and actually CNN inspired the graph convolutions. As a matter of fact, the first papers on graph that use graph structure data use convolutions as the CNN convolution, the standard convolutions that we know as a starting point, and then they hit the roadblock where they realize that graphs, the graphs, are in real world, and like social networks are different from the way we understand images. So we need to have something specialized for graphs. So just to give an idea of how they're similar and how the one idea can be confused with the other. So here's an image of an image that in typical image classification task, what we are interested in is, let's say, predict what's on the image. And the way we go about it is that, we would, or the way long ago when this problem was quite new, the way it was approached was that you would be predicting what each pixel is about, and then overall create the whole identity of the image. And then at some point, or very soon, everyone realized that predicting what is each pixel about is quite infeasible. There are lots of pixels, and it just computationally really hard. So from there, the idea of a CNN filter came about. That we would have these instead of predicting what's on each individual pixel, we would look at patches of pixel and aggregate the information. So generally, the idea would be that is that each pixel is the neighborhood of the pixel is already telling you something about the pixel. So usually like one pixel is not going to be very different from the other pixel. So we can actually aggregate the information from the so-called neighborhood of the pixel to be able to predict what's that part of the image is about. So in that way, we were simplifying the problem by aggregating the information from the neighborhood. Please do keep in mind the word neighborhood, because that's really relevant. And you would do this patching, apply this filter throughout the image, and overall get a much more simplified, aggregated picture of the image. So this would be a little bit of generalization, but computationally it will be much more faster, because now you're not looking at each pixel. You're not trying to predict everything for each pixel separately, but you're using the neighborhood information of the pixel to help improve your prediction. So now, how does it can be confused or could look similar to a graph convolution? So again, we can think about these pixels as these blobs in this picture, and let's suppose we want to predict what the red blob is about, and based on the idea of convolution, what we do is that we look at a certain neighborhood or certain neighborhood of pixels surrounding that red blob. So let's suppose if we are looking at just one hop neighborhood in a two-dimensional space, we have all these 8 pixels surrounding that red pixels that we would use to predict the value of the red pixel. So where there are different kinds of aggregations we do, either average the values from the neighborhood or take the max or min. In standard we call them average pooling, max pooling, min pooling, and so on. So looking at this picture, we can see that it exactly looks like a graph. You have a graph, you have a node, and which is like this blue blob, red blob, and you're interested in predicting the value for that, and then you have a concept of a neighborhood of that blob, and you're using the information from the neighborhood to be able to predict better. So when now looking at the picture on the right, which is a graph, as I showed you earlier, that it had these nodes or vertices and then edges between them. Again, now if you want to predict something for that red node, we again can look at the neighborhood, which is the directly connected nodes to the red ones. So it looks very similar. That the way we had the CNN, we can actually use the same idea for graph convolution. So, and yes, the basic graph convolution is the idea. The idea came about from CNN. However, the challenges that were faced in the original formulation were that usually, not usually, all the time when we have a image, we have a very regular kind of a structure around it. So each pixel is surrounded by the same number of neighborhoods. So, we have a very neat kind of a filter, which is, fixed size. So we always look at, one hop away, two hop away, and so on. Whereas in the graph, we don't have that structure. Each individual could be connected to a very different set of individuals. So, so even you would think that, it could be one concept can be used in the other, but it was really hard to generalize the simple convolutions into a graph convolution. So they had to be done in a much more specialized way. Also, images are kind of really have an order. So when you're applying this filter, you're going in a certain order, and that really is helpful in determining what each pixel is about. In graphs, graphs are what we call permutation invariant. So you can reorder the nodes in the graph in any way, and it still will retain the same structure because it contains the same connectivity. However, you can draw it in any other way, and it would still mean the same. So you don't have a scientific ordering in a graph. It's a deeper concept, but it just I don't want to go into too much detail of it, but it just overall the idea is that there are a number of ways in which a simple convolution is different from a graph convolution. So having said that, okay. Before I actually do talk about graph convolution, wow, we haven't even gotten to there, and it's we have been in this for 45 minutes. I will briefly touch on how the way we understand neural networks and the forward propagation. So usually, what you have, this is something you probably have seen. You have input neurons, you have some, and you have some output neurons, and then you have some hidden layers which have these weights that you want to train. They are represented usually by this equation. For each layer, you are predicting the values for that layer by applying some kind of an activation on a function which almost always have some weights to train, and it is fed in the values from a previous layer, and then the bias is optional, but you typically add it. So this is something you probably have seen. So just I wanted to highlight where does when we have a graph structure, where things will change. So pretty much the graph convolutions will be similar to at least like the most basic form of graph convolution. Training a neural network with graphs is quite similar to a simple standard forward propagation neural network, but now we have an added adjacency matrix or connectivity information incorporated in it. Sorry, I didn't use the word adjacency before, but generally in graphs, the way the data structure that we use to represent a graph is an adjacency matrix, which I'll show you in a bit. I'm hoping that you all might have already seen it in some form in any other classes already. Anyways. So now let's get into what a graph convolution is. So let's suppose this is our data, which is a set of nodes. Again, those blobs are the nodes, and their edges between them are the connections between them. And let's suppose we are interested in predicting something about this the red node. In standard machine learning, what we would do is that we have some certain features. So x0 to x4 are the features, characteristics of this node, and we want to predict x5, which is our dependent variable which we are interested in, and we train a model to So what we do is we'll use these individual features of that node and predict predict the unknown variable based on that the set of features of that single node. Now, what happens is in graph convolutions, we don't limit ourselves to just the features of the entity we are interested in, but we also look at its neighborhood. So the green dotted circle indicates the first hop neighbor of the red node, and they also have the same features as the red node. And let's assume no missing values. So we're not talking about how do we do the data imputation, etc. But what we would do is that we would use all the features from the neighborhood as part of our learning process for that individual we are interested in. So there are many different ways of aggregation, just the way we had for convolutions, simple convolutions, that we had these max pooling, min pooling, average pooling. There are a number of convolutional operators for graphs as well. But at the moment, just assume that what we are doing is that now for an individual, that red individual, we are not just looking at its own properties or characteristic, but of its neighborhood as well. And we can extend it to the second hop neighborhood, third hop neighborhood, and we can keep on going out in these concentric circles. So that's pretty much the whole idea behind graph convolutions. Now, and as I promised, I just wanna you won't be able to learn the whole graph convolution through this slide, but I think it's really important to understand that even if it sounds complex, it's really under the hood. It's really a very simple idea that goes behind graph convolutions. So as I mentioned, an adjacency matrix. So usually the way so this is about how you operationalize this whole concept of graph convolution. So you would typically would need some kind of a data structure to store the connectivity information or the network information. Usually in graph theory we do it with adjacency matrix. So you simply have, let's say, a binary adjacency matrix which indicates that whether two individuals are connected or not. So let's suppose if we had 4 individuals, this 4x4 matrix is telling us who is connected to whom. 1 indicates that they are connected, 0 indicates they're not connected. Then you have features, which you all are familiar with. So standard machine learning, you always have a set of features. So let's suppose we have these 2 features for these 4 individuals. Just for the sake of mathematics and logic, we would have this identity matrix, which is the kind of like these self loops, and they are just meant to make sure that an individual's own characteristics or features are accounted for when we are doing all the multiplications. And then W we have, which is like our set of weights. So these are our weights associated with these set of features, and this is something that we want to train, that how much are certain features reflective of the output we are interested in. Then D is basically just the diagonal matrix. Is a summation of degree of A, the matrix on top, and this is just used for normalization, because just the way we have in our standard machine learning, when we want to normalize our features so that none of them are skewing our results. Same as that we don't usually. If you had any exposure to graph theory, you would have heard this term that this power law distribution, skewed distribution. So usually the way we look at networks is that they're always very skewed. There are certain entities which are highly connected, and then most of the entities are not very well connected. So you have a very skewed data. So this D, or the degree matrix, is multiplied with the adjacency just to normalize thing. And all we literally do is, even if you ignore the part about standardizing or normalizing things, all we are doing is multiplying our connectivity with our features, and basically using the neighborhood features as an indication of an entity's feature. So now the entity's feature are no more its own individual feature, but are the features of its neighborhood. And just to give you, to warn you, this is just one way of doing graph convolutions, and basically it's like the most basic way of doing it. There are way more advanced way of message passing and sampling that have been introduced in the last few years. So this is just meant to show you that it's the basic idea is quite simple. And as I showed you in the last slide, so simply, when you are calculating the values over different layers of your multi-layer perceptron, you typically just have this feature vector multiplied with the weights, but now you have this adjacency, and the rest adjacent identity, and this D inverse is just for the sake of making sure that the things add up properly. So this was all, it was meant to show that it might sound complicated, but it's quite, like, the idea is quite simple and straightforward, right? So yeah, that was pretty much what the basic idea was. And now I think I will move on towards something more interesting and something that would be that would show you where in a real world setting this concept can be applicable. So Twitter, for example, let's suppose you have a problem of identifying who are hateful and non-hateful users. So this is something Twitter is typically very interested in. Usually, like, they are blocking people based on, what kind of language they're using. Is it divisive? Are they using some coarse language, some terminology that's hurtful, politically incorrect, inciting violence and whatnot? So, all those kind of things. And they typically are always looking for differentiating individuals based on, what kind of speech they have. Now, what happens, so the question is that, like, how do you actually do that, go about doing it? So, yeah, and the way they operationalize it is that, people are, let's suppose we have all these Twitter users and they're tweeting things. Some of their tweets will be negative, which is that, they're using certain languages which are not really appropriate. And, for the most part, you hope that, they are talking about cats, let's say. So the question is that, whether how do you label each individual as to whether, they are hateful or non-hateful, or, they are divisive, or they are inciting violence and whatnot. Now, and by the way, yeah, if you want to try this problem, the data is available on Kaggle, and you can, and there are lots of solutions out there. There have been papers that have been written about it. So, you can see that how people have tried to tackle this problem. So, for example, this was one of the papers that that I know of, which used graph structural information, not as an explicit graph, but used certain calculated certain properties based on the connectivity or retweets of individuals, and used that as their features, and showed that those sort of features did help. So from there, my group, we thought about that, why not we use graph convolutions directly, and try to see that how those sort of features could, just using GCN's graph convolutions network, could be helpful. So overall, this data, the one on Kaggle, has over 100,000 users. Out of which only 5,000 are annotated as hateful or normal. So by annotation, what it all means is that somebody or some set of individuals sat down, went through a whole bunch of tweets from about 5K individuals, and labeled them as whether they were hateful or not hateful. And you can imagine what a huge task it would be to just go through tweet after tweet after tweet, and overall determine whether an individual is hateful or not hateful. And the idea of the way these are labeled is based on like certain set of words that Twitter would tell them that those are the words that are acceptable, unacceptable, and maybe they will calculate they'll do some frequency word cloud, and determine that even individually each individual is whether hateful or not based on how frequently they use certain words that are acceptable and non-acceptable. However, so the annotated data is only about 5K, and there are about more than 95,000 other users which we don't know whether they are hateful or not. And the question here is whether we can do machine learning or automate this process of labeling these individuals, given what we know about this 5K user, whether they're hateful or not hateful. And this is a classic semi-supervised learning problem. Now, the features that are associated with these individuals are derived from their tweets and their activities, and this is, I think, from the paper above, if I remember correctly. So, they were using about 205 features that were extracted by doing some natural language processing over the text of these of individual tweets of these individuals. So in a classic machine learning setting, what you would have is in a semi-supervised learning method, you will have you will be given a data set with a set of features, and some of them are labeled already labeled as hateful and non-hateful. In this case, you have 5K of them. You would train a model that would determine for you or predict for you whether the labels for the rest of the individuals. And just like a standard machine learning technique, you will do performance analysis, how well your model is working. Now, where graph convolutions come in, and you can find this demo on the Stellar Graph library and play with it, is that we were using information about the retweets done by each individual. So now we're not just using those 204 or 205 individual features, but using the information about who is tweeting, retweeting, or tweeting somebody else tweets, or forwarding those tweets, in other words. What this tells you is that, even when you have a fragmented information, this retweet behavior can be indicative of the inclination of the unknown individual, whether they're hateful or not. So overall, that idea, so those retweets improved the model performance over standard machine learning method. And you can have a look at it at the demo, but this was just meant to show you that how these how a graph structured data could add value to your standard machine learning toolkit. Now, what we tried was the standard GCN, the way I explain it, and in a single layer, it is represented as the retweet structure of the graph, which is given by this graph structure, A prime. The features, which are the standard node features, and the trainable weights are what we are interested in after. And of course, like in any standard machine learning methodology, you do apply some kind of non-linearity, and you output your prediction. So something for the hidden layer, and eventually, for us, this was a classification task, a binary classification task of whether individuals are hateful or not. There are other methods you can do it. So just in 30 seconds, you could, the way this simple GCN was about, aggregating the neighborhood information by actually doing this matrix multiplication. But there are other ways you can do this aggregation, which is just concatenating the features from your neighborhood. So what you do is that now, instead of squishing the values together, you have an expanded set of features corresponding to each entity. I am sure this would be lost on you, but it was just meant to show you that there are multiple ways of how you can do graph convolutions. Now, the last part is about this traffic management system that I helped build for the Transport for News. Actually, no, this one that I'm talking about is about the Sydney Trains project, which is about predicting forecasting frequency of surfaces of the train lines. But before I get started on that one, I just wanted to give a short idea of where in forecasting, deep learning on graphs can be useful. So usually when you look at forecasting, we think of some kind of a time series, and we have some historical information, and based on that, we predict something in future. So for example, if you want to predict the weather for tomorrow, what you would typically build a system based on the historical weather. So maybe you look at weather for the last week, last month, last 1 year, and last season, etc. And train a model based on that historical information, and forecast something in future. Again, if you haven't picked up but the underlying assumption that we have there is that each entity is independent. So for example, if you're doing weather prediction for each city in Pakistan, you would be using historical sorry, what did I say? If you're doing weather prediction for each city in Pakistan, you would look at the historical weather for each city individually. Now, this usually works fine, but there are systems where things are connected. So even if in this weather application, the cities that are adjacent to each other or close by, their weather is already indicative of how the weather would be like in their neighborhood. So there's a natural connectivity, natural network that is there, and if we have that sort of information, why not use it? And there are many applications that you would see improvements based on using that that neighborhood information. So some of the applications of it are traffic management. So, for example, predicting speeds on road segments. This was a project I did last year with the Transport for New South Wales. We were looking at the Victoria Road corridor here in Sydney, and using the Google travel time data of speeds of travel time of average travel time of vehicles on each road segment in the Victoria Road corridor. And the question was, can we forecast what would be the traffic like in the next 15 minutes, 30 minutes, 45 minutes, 1 hour? And the more interesting question was, what happens when we have incidences like an accident happening, or a construction or road segment closing because of a construction, or traffic jams and whatnot? How would that affect the forecast of the speed? And this is actually where the graph structure plays a really crucial role, because when you're looking at each road segment independently, you don't have information about what the neighborhood of that road segment looks like. You don't, if there's an accident at any intersection, which is a little far from a particular road segment, if you're training a model just by looking at focusing on just the history of that road segment, the traffic conditions on that road segment, you will miss out the details about what it looks like in the neighborhood of it. So what if like an accident happens somewhere far? How would that affect this road segment? So you can naturally see that how a graph structure data would be helpful in improving such a system. Similarly, the project that I just did finish the first part of it, and I would be using as a running example is in the domain of public transport systems. So train lines, they're interested in frequency of services, how many trains are stopping at each station. This is important for them for understanding the demand forecast, like which trains need to be rerouted, where they need to make extra stops, if they want to skip some trains, some platforms, and so on. So these are the sort of things where they would need that sort of information. And you can see that any train line is already, there's a network, train runs on tracks and they're already connected. So there's already a dependency. And if we have that sort of information, that which train stations, which are the train stations coming ahead or before, that sort of the information from those stations could always help improve the system. Otherwise, rideshare systems like Uber, etc., they need these kind of systems to predict the duration of trips, usually for determining the costs associated with those trips, etc. Similarly, in retail business, sales and demand forecasting is where you would such a system which is using not just historical data but also the proximity or graph structure data would be helpful. That for example, if you have multiple for a chain retail store, if you have multiple stores in a closed geographical region, you probably that could what's the demand or what's the sales like in those other all the different shops could help build a better system. So overall, when you're doing this building such a forecasting system, you have two components. The more standard one that we know about is the temporal one, which is usually the historical information about the entity we are interested in predicting. And usually that temporal information is helpful in determining, whether there are some kind of periodicity, some kind of seasonality or some trends, upward moving trend or downward trend, etc., etc. However, when we have the more the more interesting scenario is when we have unexpected situations. So, incidences like accidents or traffic jams, etc., are something that are usually the temporal information doesn't give. Even if they capture it, they are not able to reflect it in the future predictions very well. However, when you have the more interdependent connectivity information, those sort of information could really help improve the system. Here's just a toy example. Let's suppose this is a train network, and this is a particular train line. The sort of data I use is that I would have historical frequency of services at some granularity about these stations. So, for example, every 15 minutes, how many trains are stopping on each station? And the question I would be interested in answering is, what would be the frequency of the service in the next 1 hour? That would be something, kind of an information that would be helpful for a traffic controller. Without having the network information, the way we do forecasting is as a machine learning problem is, again, we assume that our historical information is some kind of given to us like a table. It's the difference between forecasting and a standard machine learning problem is that usually you have the same features over time, so you have a temporal aspect to it. So, for example, here we have all these vertical blobs are, let's suppose, are train stations, and then x0 and x5 are the historical frequency of services on these stations. And just using this information, what we would be doing is that individually predicting what's the speed, what's the frequency of service in the next hour or next 2 hours, and so on. But when it comes to if we have the structural information, we can use not just individual frequency of services, but the frequency of service of the entire network to inform us and build a better system overall. So this was the way we operationalized it, is that for the temporal features, we use the standard RNN, recurrent neural networks, and more specifically LSTMs to train the model on. And this is something more standard, something more familiar with to everyone, that how you do time series forecasting using a deep learning model. And within an LSTM cell, what you have is that your previous you have a sequence of cells. Each of them are maintaining some kind of a state and forwarding that state to a future cell. So at each point you are using historical information from previous cells to predict something in future. Now, when we have spatial features, we can apply graph convolutions layer on top of it. So now in time, we are aggregating the neighborhood information of a node. So let's suppose if we were trying to predict the frequency of service of the blue nodes, we would in one layer of convolution, one convolution layer, we would be looking at one hop neighborhood and aggregating the neighborhood information to predict the frequency of service for that blue node. And structurally, in a deep learning model, this would be a different set of layers on top of the standard LSTM layer, which we use for forecasting. So the difference is that now we just don't have the historical frequency of services, but we have the connectivity information of how these different stations are connected through this adjacency matrix. And we would do these graph convolutions, which is basically the way I explained earlier, that you have the connective information and the feature information, and you aggregate them somehow. Either you multiply them, you concatenate them, or apply other sophisticated method, but you somehow combine that information together and then feed it to the LSTM layer, which is meant to work on sequential data. So yeah, I didn't go into too many details because there was too much to cover for this talk. We can discuss it. I can discuss it with Hamad at another time, that maybe I can go in more detail about this method. But this was just meant to give you a basic flavor of how it works. So just to summarize, I talked about deep learning on graphs in general. If you go now and start searching for this concept, you would find them in referred to by different terminologies. So they're also called geometric deep learning. That's actually a more technical term for it. Graph representation learning is also very frequently used, and less frequently used is a relational inductive biases, etc. But you'll find many other different ways it's been referred to. Overall, I talked about graph convolutions and how they are inspired by CNNs, and what are similarities and where CNN basically falls short. So, and how a basic graph convolution look like. And then I tried to really quickly go through some interesting real-world examples that that might look interesting. I couldn't really touch on a few things. So basically, if you want to go and try graph machine learning, where can actually you can find any tools? So just the way if you are familiar with Keras, you know that you can already build models using using CNNs or LSTMs, etc., because those tools are already available in those frameworks. Unlike graph convolutions, which are still very new and not that readily available, so you usually typically have to go and code a whole graph convolution. However, there are certain libraries. So PyTorch Geometric is a PyTorch-based library which has graph convolutions implemented. DGL is really popular. That has a number of methods for graph convolutions, and of course Telegraph, the library that me and my team had been building, has number of graph convolution methods. I would highly recommend it. Do check it out, and feel free to talk to me if you are interested in using them, or if you have a problem that needs graph convolutions. Also didn't talk about standardized benchmarks. By that, what I mean is that right now this field is really all over the place. There's not even a consensus on terminology. So it's really hard to understand which method works where and why. So usually you would, just the way in any typical academic settings, every paper thinks that what they're building is really better than anyone else, and all you have is what they are saying, or what they have tried on their data set, and how they have fine-tuned their hyperparameters. So you don't really actually know if the comparison is fair. So we lack that, and that makes it a little challenging for graph convolutions to be useful. Unlike CNNs, which images are sort of standard, so it's easy to have like some basic benchmark data sets and compare all the methods on the same data set and say, okay, which works better. Graphs are really usually very challenging. We don't have a standard graph data to work with, so it's hard to compare different methods. Scalability, and I misspelled scalability. So that is basically about, the problem is that now when you have to productionize any system, you want to be able to train it on, a huge amount of data. For most of the machine learning method, you can use parallelization. With graphs, because of the connectivity, it's still very challenging. How do you actually parallelize the system? Because, if you can imagine it, that for each entity, you need to have a complete network information and information about a neighborhood of that node, however wide neighborhood you're looking at. So usually you have to do some kind of sampling, and it's not very easy or straightforward. And lastly, dynamic graphs. So usually when we talk about these networks, the problem is that we simplify things by saying, we have a snapshot or a static view of a network. So think about transaction networks. Transactions are all happening every second. The network is not static, but if I have to analyze it, I would just look at one particular aggregated snapshot of it and use that as my data. But reality is quite different. So how do we extend these methods to evolving graphs is something that is barely touched. So when I mentioned these spatiotemporal methods, that's pretty much the only place where I know or I have tried using some sort of dynamic information, which was the historical information, to do something like forecasting. So yeah, that was all from me. I apologize for being too rushed and fast. I do have a tendency of talking really fast, but I just wanted to capture, give you an overall picture. I hope it still made some sense. Yeah, that's all from me, and I'm happy to take any questions.
Thank you, Dr. Habibah. That was really insightful. And I don't think it was very fast, by the way.
Okay, but I do have a problem. I know. I'll be the first to admit that I talk very
So
fast.
we do have a few questions that were asked during the course of the presentation, but I thought it was better to ask at the end. So Taimur, are you there? Can you go ahead with your question?
Yes, sir. Assalamu alaikum. Uh,
Walaikum.
my question was, you mentioned about going through levels of neighborhood. So when you would usually examine a financial network or any other network, so there would be generally be endless levels. There would be one transaction and there would be another transaction, another level and another level. So till what limit do we go? Is there any rule of thumb, or where do we stop looking?
Uh, it's an excellent question. So this is actually kind of like a hyperparameter that you train. So you don't know how far or deep you need to look. What you would do is based on your data and the application you're studying, you would try one hop neighborhood, two hop neighborhood. So, and right now I give you like a very basic idea. There are methods in which you can actually skew the neighborhood as well. So instead of looking at, like the all the neighbors from within one hop, there are methods which have trainable parameters where you can actually see that where you need to pay more attention to, as opposed to looking weighing everyone equally. Uh, so and similarly, their graph attention, just the way the attention mechanism works in general with machine learning. There are ways in which you can actually see train the models to learn which are the more influential entities to pay attention to. So yeah, this is something that you don't know beforehand. You can start with something simple, that let's look at one hop neighborhood, two hop neighborhood. Of course, the more neighborhood you add, the more complex your model becomes. Complexity is good, but of course it's add computational cost as well. So you have to balance it against that.
Okay, thank you.
No problem.
Questions from other master's students before we move to the my lab. So for other master's students, if you have any questions. Okay, Nadia, you can go ahead.
Yes, ma'am. Hello, ma'am. Ma'am, my question is about the normalization. Um, Actually, I just want to have some suggestion on if we have already a complex and graph network, and we want to reduce the complexity of our model, then isn't that better to before to apply the normalization, we are apply the network segmentation, we segment the a different part of we segment the networks, and then we apply the normalization on the inner boundaries between the segment to segment. Isn't that better option?
So what would you mean by segmenting your data or your graph?
Um, Ma'am, if we have multiple features in our network, and then we apply some sort of to we have some some feature is more apparently enhanced for few persons, but not for some groups, and then we apply the segmentation on the basis of the feature apparent, and how the feature enriching the and more significance for a specific group, and then we apply the normalization on only that's boundaries between the segmentation between the groups. uh,
Sure.
isn't that for to
So
reduce the complexity of the already complex big network and graph network?
certainly, this would help make it more tractable, more feasible to train the model on. However, what you have to be careful with is that, and this is something I mentioned towards the end and didn't talk much about, was scalability. That the problem is that usually you will need the network information, and you need it to be complete in certain ways so that you can actually train the whole model. So, without the graph, you typically can look at each entity separately, right? So you can do the feature pre-processing, normalization, etc. Beforehand, and then you can sample your data in any way you want and can train the model on batches. Now, when you have this added feature of graph structure within a sample or a batch, or probably when you say segment, I'm assuming this is what you meant, you would need to have a complete information of the network for that particular sample of your data. So you have to be a little smarter about how do you actually gonna sample the graph. So I'll give you just one example. I was looking at this open corporate, it's called Corporate Office or something like this. It's a UK company registry, registry data. It's open source. And I was looking at, officer in predicting labels for officers which are disqualified based on, different, different reasons. The thing was that, again, this was a huge network, and I could only sample a limited set of data at a given point. But then I had to see that what radius of neighborhood I am focusing on. So the way I would sample my my data for training would be based on that if my neighborhood should be complete for the set of entities I'm looking at any given point. And yeah, once you have that, you have a device a sampling strategy, which again involves some thinking about how you would go about it. But once you have done that, you can, of course, like within that sample, do all the pre-processing and everything independent of the other samples. I hope this. So yeah, there are ways of doing it. It just, they're not really very standard, and these are kind of like systematic choices that you have to make and see if they help or if they make your model worse. So you decide accordingly. Did that answer?
So Salman, go ahead with your question number 1. Question number 2 we can discuss later.
Okay, Assalamualaikum. So my first question is, I applied the concept of GCNN by using NetworkX library and PyTorch with the concept of message passing neural network in predicting molecular properties on Kaggle. But in all these data sets, we do have basically neighbor connections. We do have data of neighbors, that one node is connected to all other nodes and their values. But is there a possible way that we can back propagate through labels to generate neighbor connections? Like, for example, if I have 1,000 genes, and by giving a medicine to a patient, one gene is getting high, and on the basis of that gene, another gene's value is getting low. So can we generate those connections between nodes based on labels, like interactions between nodes?
Wow, that's a very interesting and excellent question. So the thing is that for these methods, these are inductive methods usually. And by that, what I mean is that you can definitely infer missing information, so missing links, but you have to start by providing it with some ground truth. So even if you just cannot just blindly or at least like in my knowledge or my how much I've used it, it's not that you have absolutely zero network information and somehow you can infer the network from just the attributes or the features of the entities. I haven't seen any such thing. but it's a it can work in a semi-supervised situation where you provide it with some labeled sample data. So, for example, some small set of data for which you have both the entity information or the entity characters features as well as some as a connectivity information available. And once you've trained the model, you can do the standard link prediction on the rest of the data for which you have missing links. So, this is how you would do missing link imputation using these kind of approaches. But I don't know of any methods where you would actually have no network information and would try to build the entire network out of it.
Okay. I tried to solve this in a way like by connecting each node with every other node, and by setting their weight to 0.5 and back propagating those weights as my weight matrix of GCNN, so that it can back propagate to some local minima or something like that to converge. But there was nothing good. So another thing I tried was to multiply each node with every other node, like polynomial features, like generating polynomial features. So that worked much better than this, but that is too much expensive computationally. So if there might be a way to solve this, then
yeah, that will
help a lot.
So, actually, this is something I'm dealing with at the moment. The tracking project that Hamad mentioned at the beginning is basically about tracking deformable objects over time. And I don't have, so I have these video feeds out of which, we can slice them in frames, and I have objects detected in each frame. And now I want to be able to track an object over time. So I basically need to create this graph within those frames, so that objects detected in one frame are connected to the objects detected in the next frame, and so on. There's a whole problem with these object detection because these are deformable objects, and there are lots of occlusions as well as stacking going on. So that's a different problem. But at the moment, I am trying to figure out how I can actually predict links between these different frames and connect the objects in one frame to another. But at least in my search in the last few weeks, I haven't come across any method which would help me, predict a whole network out of just using, the features that I have from object detection. So, but yeah, it's a problem to solve.
So this leads us to very nicely to Umair's first question. Umair, can you go ahead with your first question?
Yes, sir. I have two questions. The first one is related to noise in the graph networks. When we are talking about protein interaction networks, more of the links are noisy and some links are missing. Then how we can cope with this problem when we have noisy data, graph data?
So this would be a problem of trying to infer the links, right? Predict the link, correct?
Yes.
So some links might be false as well, and some might be missing. So the noise is both ways, positive and negative.
So basically, some links that shouldn't be there, and some links that should be there but are not there.
Yeah. Yep.
One strategy that I can think off the top of my head is that use the clean data to train the model on, and then try to infer the missing links of the rest of the data. That would be one way of training a model that is not using a lot of noisy data. There are some random walks methods as well that are more probabilistic. So methods like graph sage, in which what you start with is that you in your network you do these random walks, like probabilistic walks, starting from each target, your source or target, whatever you want to call it, node, and then you do multiple walks. So the assumption is that you will be unless like you have a lot of noise in your data, you would be actually have a good sample of your true walks in the network and lesser samples of false walks with noisy links in them, and using those samples as your starting point tend to work uh, uh, well in many domains. But again, the problem with noisy data is that it's kind of really subjective. That where how whether it will actually be like garbage in and garbage out. You don't if that information is really gonna mislead the model. So
Right.
if I had to do it, I would try to just use the data I'm confident about to train a model on, and then try to infer the rest of the links. As a question, I mean, so you already have the information about what are the faulty connections, right? So
We know the percentage of noise, but we don't really know which ones.
which one is that?
So there is an estimate of the noise, but we don't really know exactly.
Okay, so can we apply feature attention after that, so that we can filter out noisy features that we are selecting in our aggregation function based on that feature attention? There was a paper, I think, FAGCN in 2019 that did something like that.
Graph attentions. What I know is that even in that situation, so basically the way the graph attention works is that the way what they're doing is they're learning the weights of where to pay attention to. So it really again depends on how much noise is in the data and whether this would how much it would affect the outcome. So I don't think that they can GAT can automatically differentiate which features to pay attention to unless there's some information about where is the noise and where isn't. I mean, if there are any features that that you can add to the data which can help indicate that whether this is this could be this link or is something that is questionable.
Yeah, we can have a confidence score. We do have a confidence score.
Yeah. So in that case, yeah, probably this can help.
ठीक है. Go ahead, Umair, for your last question.
Ma'am, when we are talking about semi-supervised learning, basically we are predicting the label of the unknown example. Basically, we are predicting unknown label from the information of the known data. When we are talking about the KNN model, the same strategy is applying. We are trying to capture the information of the neighbors and trying to predict the label of some node. The GCNN is working in the same way. Is there any difference between these two strategies for semi-supervised learning?
So so the k-nearest neighbor, they look at they try to minimize the distance between one hop of neighborhood, right? Whereas GCN are meant to be flexible, that you can look at as you can look at as many at a bigger radius of your neighborhood. So I think this is one of the places where they would be different. Yeah, I think.
But for
Yes.
KNN, we can also increase the radius of the neighbors, right?
Yes, we can make it more flexible. But yeah, let me think. Nearest neighbor. So essentially, they're in a way different from that. For the k-nearest neighbor, you start with some predefined number of classes, okay? And sorry, not k, but the number of neighbor. Okay, yeah. So
Yes.
So usually, yeah, I'm actually like trying to recall how KNN works actually. So usually you would do it without any graph information. All you have is a certain set of features, and you do in some Euclidean multi-dimensional space based on the feature, you calculate the distance between those entities.
Right.
So the goal is in that case is primarily just for classification, right? Whereas GCNs are meant to be used for anything. So you can predict node attributes. So KNN, yeah, like that would be one difference. KNN you can't use to predict features, right? Whereas a GCN you use to predict attributes on nodes or edges, or maybe I haven't thought about comparing KNNs with GCN as such, but I would think that maybe GCN, when you're doing node classification, probably they're quite similar to KNN, given that KNN can be generalized to multi-hop neighborhood. But otherwise, for other tasks such as link prediction or attribute prediction, I don't know how would you use a KNN in that setting. Does that make sense?
Yes, ma'am. It's almost clear.
So do we have any other questions? Chat में तो यही थे questions. सलमान, आपके लिए डॉक्टर किफायत का कोई मैसेज है वो देखिएगा. If there are any other questions, we can ask right now.
Or feel free to, like, if you guys have any follow-up discussion and have further questions, I'll be happy to answer them at any point. Or Hamad, I'll be happy to continue talking about this thing or anything that you think could be relevant in future.
Yeah, we're going to try the stellar graph pretty soon क्योंकि एक दो questions काफी अच्छे बन रहे हैं. So we're going to try, and if we get stuck or if we want some more help, we'll definitely come back to you.
Oh, I would love to. I'm basically the project has finished in June. Funding khatam ho gayi. So we are and the team has now moved on to different thing, and that's how I'm getting into this computer vision tracking thing. It's a different project I'm working on with a different team. But overall, I still enjoy. I'm in this other tracking project as well. I'm trying to bring in graph machine learning. So I'm always interested in problems and use cases where graph machine learning could be applicable, and would be happy to fill you guys up with the methods in stellar graph or any other methods that I have come across that could be relevant. I will certainly think more about the question of how you can infer the missing links, especially like when you don't have any graph information. Is there any methods in graph machine learning that can infer the graph data? Because that's something the problem I'm facing, that how actually we can even build a graph and when there doesn't even exist one. So is there any deep learning methods that could be used for it? So if there mujhe koi idea mila, so I will certainly share it with you.
Perfect. Thank you so much. If there are no more questions, so I'd like to thank Dr. Habibah again for taking so much time out of her busy schedule, and that too on a Sunday. And thank you so much for this, and inshallah we'll be in touch. The assignment for this seminar is going to be up after your midterms, so you can prepare for your midterms first, and then we'll talk about this seminar again.
Thank you guys for having me. I really enjoyed it, and it was a really good exercise this morning, trying to put all my thoughts together. It was a good refresher. I enjoyed it, and I would be